The variation of properties during phase change processes are best understood using property diagrams. In this presentation, we will focus on the liquid and vapor phases and their mixtures by discussing two important property diagrams. We will first look at temperature as a function of specific volume, or a TV diagram, and then at pressure as a function of specific volume, or a PV diagram. Recall that specific volume is simply the volume of a substance divided by its mass. Its units are meters cubed per kilogram. Note that specific volume is simply equal to the inverse of the density. Consider a cylindrical vessel which contains some amount of a pure substance in the liquid phase. Now suppose that a piston is allowed to rest on the liquid such that it is at some pressure P1. We want to plot the temperature of this substance as a function of its specific volume as energy is added to it and it changes phases. Let's say that this liquid is at some initial temperature T1 and has an initial specific volume V1. At this state, it is called a compressed liquid. A compressed liquid is one which is not about to vaporize. If energy is added to the system in the form of heat transfer, for example, the temperature increases and the liquid begins to expand, increasing its specific volume. Note that throughout the heating process, the piston is allowed to move as the liquid expands, so the pressure remains constant. If enough energy is added, it will become what is called a saturated liquid. At this point, it is still a liquid, but any additional energy added to it will cause some of the liquid to vaporize. The temperature of a saturated liquid is called the saturation temperature, and the specific volume is denoted by Vf. As more energy is added to the system, some of the liquid begins to vaporize, increasing the specific volume. However, note that during the vaporization process, the temperature remains constant at the saturation temperature. At this point, the substance has both liquid and vapor phases. This is called a saturated liquid-vapor mixture. This mixture is said to have some quality. The quality is a number between 0 and 1 and is defined as the ratio of the mass of the vapor over the total mass of the mixture. The quality of a saturated liquid is 0 because there is no vapor yet. As more energy is added, more of the liquid vaporizes, increasing the specific volume. At the moment all of the liquid has vaporized, the substance becomes a saturated vapor. Any heat lost at this point will cause some of the vapor to condense and change back to a liquid. Note that a saturated vapor is still at the saturation temperature. The specific volume of a saturated vapor is denoted by Vg. Because all of the mass is in the vapor state, the quality of a saturated vapor is 1. As more energy is added, the vapor continues to expand and the temperature begins to increase again. This state is called a superheated vapor. Remember that the pressure has remained constant throughout this phase change process. Let's repeat this entire process. However, this time, suppose that more weight is added to the piston so that the substance is at a higher pressure. The specific volume of the compressed liquid is slightly smaller at this higher pressure. Also note that as the pressure increases, the temperature at which the substance begins to vaporize, or the saturation temperature, increases. As pressure increases, the specific volume of the saturated liquid increases, while the specific volume of the saturated vapor decreases. As the pressure is further increased, the saturation line continues to shrink until the saturated liquid and saturated vapor states are identical. This is called the critical point, and the pressure and temperature at which this occurs are called the critical pressure and critical temperature. At pressures above the critical pressure, there is no distinct phase change. A line can be drawn through the saturated liquid and saturated vapor states, forming a dome which separates the different regions of the property diagram. On the left side of the dome is the compressed liquid region. Under the dome is the saturated liquid-vapor mixture region, and on the right side of the dome is the superheated vapor region. The line on the left of the critical point is the saturated liquid line, and the line on the right of the critical point is the saturated vapor line. We will now look at a different property diagram called a PV diagram, which shows the pressure as a function of specific volume. This diagram is similar to the TV diagram. Suppose that we have a piston cylinder device which contains a compressed liquid at a fixed temperature T1 and at an elevated pressure. We slowly decrease the pressure by removing weight from the piston, and we allow heat transfer between the liquid and the surroundings such that the temperature remains constant. The pressure of the compressed liquid decreases and the specific volume increases until the substance becomes a saturated liquid, at which point any more energy added will result in the start of vaporization. The pressure at this point is called the saturation pressure. Just like before, the specific volume increases from Vf to Vg as the saturated liquid becomes a saturated vapor. As the pressure is further decreased, the specific volume continues to increase and the substance becomes a superheated vapor. Remember that energy transfer is occurring throughout this process so that the temperature remains constant. If we change the temperature of the substance, the process follows a similar path. Just as we did with the TV diagram, we can draw a line through the saturated liquid and saturated vapor states. The various regions on the PV diagram are the same as those on the TV diagram.